If a laptop is lost on a train or a password flies across a crowded coffee shop network, the same question comes up. Could someone read it? Encryption is the reason the answer can be no. In plain English, encryption is a way to disguise information so that it looks like gibberish unless a secret key is used to unlock it. Take a message that says payroll.csv and transform it into something that looks like random noise. With the right key, it can be turned back. Without the key, it's useless. Here's the thing that makes encryption different from everyday privacy tricks. Hiding or deleting data tries to keep people from getting a copy in the first place. Encryption assumes someone might get a copy and still makes it safe by rendering it unreadable. That shift, from trying to block access to making access meaningless, changes the stakes. Why care about this? Because data lives in two worlds. Sometimes it's sitting still, saved on a laptop, a server, or a cloud bucket. Other times it's in motion, crossing the internet from a browser to a website, or between microservices inside a company network. Thieves and eavesdroppers target both states. A stolen hard drive can reveal a database full of names. A fake Wi-Fi hotspot can capture logins. Encryption is the lock that tries to protect both the sitting and the moving versions of the same information. One practical picture helps anchor the idea. Think of data at rest like valuables sealed in a safe. Even if someone grabs the safe, the contents stay protected unless the combination is known. Data in transit is more like shipping that safe across town in an armored truck. The cargo is already locked, and the truck adds shields for the journey. Different risks, different protections, same goal. The valuables should only be readable by the right person at the right time. Let that sink in for a moment. The goal is not secrecy for secrecy's sake. It's control. Who gets to turn ciphertext back into meaning? So how does this actually work without drowning in math? The moving parts are surprisingly simple to name: algorithms, keys, and protocols. The algorithm is the method for scrambling and unscrambling. The key is the secret value that drives the algorithm, like a combination for the safe. A protocol is a rulebook that says when to use which method, how to trade keys safely, and how to check that both sides are who they claim to be. Start with the two states. Data at rest means information that's stored on a laptop, on a phone, in a database, on a backup drive. Data in transit means information moving between systems, crossing a network cable, hopping between routers, or traveling through the air over Wi-Fi. When data is stored, speed and coverage matter. Whole disks, files, or database tables can be sealed using fast algorithms designed for bulk protection. A widely used example is AES, the Advanced Encryption Standard, often with 256-bit keys. That number describes key length, not a password length. A 256-bit key space is astronomically large, which is what keeps brute force guessing out of reach. The crucial detail is that the same key is used to lock and unlock. That's called symmetric encryption. Symmetric means one secret key does both jobs, encrypt and decrypt. It's fast, which is perfect for protecting big piles of data, but sharing that secret safely becomes its own challenge. If a copy of the key leaks, the safe can be opened. Now switch to data in transit. Here the focus expands beyond secrecy to include identity, knowing who's on the other end, and agreement on how to talk securely. The internet's workhorse for this is TLS, Transport Layer Security. It's what puts the lock icon in a browser. TLS starts with a handshake that uses a different style of math called asymmetric encryption. Instead of one shared key, there's a pair. A public key that anyone can see, and a private key that's kept secret. The public key can be used to start a secure conversation, but only the holder of the private key can complete it. This solves the "how do we share a secret key without shouting it across the room" problem. During a TLS handshake, especially in modern versions like TLS 1.3, the two sides prove identities using digital certificates, pick strong algorithms, and agree on a fresh session key. Once that's set up, the heavy lifting returns to symmetric encryption for speed. The handshake is like checking the driver's license and agreeing on a route. The symmetric key is the truck's armor for the rest of the trip. Here's what actually matters here. Symmetric methods protect bulk data quickly, which makes them ideal both for at-rest encryption and for the ongoing stream of encrypted network traffic. Asymmetric methods are slower, but they shine when bootstrapping trust and exchanging keys safely over an untrusted network. Protocols like TLS combine the two to get the best of both. Zoom in on at rest for a moment. On a laptop, full disk encryption means the entire drive is unreadable without the proper key or passcode. If the device is shut down and stolen, the data remains scrambled. On servers, file-level or volume-level encryption can protect subsets of data, and databases can encrypt tables and fields so that backups and snapshots don't reveal sensitive content. Some systems encrypt transparently, meaning the operating system or storage layer handles encryption without needing application changes. Others encrypt within the application itself, which can give finer control over who sees what, even from administrators. So the simple version is, at rest encryption keeps stored data unintelligible if a disk is lost, a snapshot leaks, or someone gains raw access to storage. Now glance back to in transit. When a browser visits a banking site over HTTPS, that S at the end signals TLS is in use. The client verifies the server's certificate, issued by a trusted authority, to make sure it's talking to the real site. Keys are exchanged safely during the handshake. Then every request and response is encrypted with the session key, shielding contents from eavesdroppers on the network. Inside companies, the same idea protects service-to-service calls and API traffic. Even within a data center, encrypting traffic cuts off easy wins for attackers who might have found a foothold on the network. Across both worlds, keys are the crown jewels. Creating strong keys, storing them in secure hardware or managed key services, rotating them regularly, and revoking them quickly if something goes wrong. This discipline is called key management. The math behind AES or TLS is rarely the part that fails in a real breach. Keys left in code repositories, credentials pasted into chat, or encryption turned off in one corner of a system. Those are the cracks that matter. An example makes this concrete. Picture an analyst uploading a 1 GB customer file from a laptop into a cloud storage bucket. Before the upload, the file can be encrypted locally using a symmetric algorithm like AES 256. That produces a ciphertext file on the laptop, still a file, just unreadable without the key. When the upload begins, the browser connects to the cloud provider over HTTPS, which means TLS negotiates a secure session. The handshake uses asymmetric techniques behind the scenes to agree on a fresh session key. With that in place, the actual upload is protected by fast symmetric encryption. At the cloud end, the encrypted stream is decrypted by the transit layer, then the file is written to storage and encrypted again at rest using the cloud service's own keys. Later, when a teammate downloads the file, the process runs in reverse. Transit is protected by TLS, and access at rest is controlled by who holds permission to use the storage keys. On a modern laptop, a gigabyte of AES encryption takes seconds, and a TLS 1.3 handshake completes in less than a second, which keeps the whole flow snappy. What matters here is that the file is protected 3 ways: sealed before it leaves the laptop, shielded on the way across the network, and stored as ciphertext in the destination. Defense in depth ensures that a slip in one layer doesn't expose everything. There's a maintenance story that goes along with this. Keys aren't set and forget. Rotating keys, retiring old ones, and generating new ones on a schedule limits the damage if a key is ever compromised. It's like changing the combination on the safe and swapping the truck's route. If a key from last quarter leaks, only that window is at risk. Revocation is the emergency brake version, marking a key as invalid the moment suspicious activity shows up. Put differently, encryption without key hygiene is a strong lock with the spare taped under the doormat. A few trade-offs are worth knowing, not to scare anyone off, but to keep expectations grounded. Encryption uses CPU time. Symmetric encryption is efficient, and modern hardware often accelerates it, but there's still overhead. Asymmetric operations are heavier, which is why protocols only lean on them during the handshake. Systems that push a lot of data, streaming video, massive database queries, care about these costs. Profiling helps decide where to tune. Another limit, encryption hides content, not everything about the communication. Metadata, like when data was sent, how big it was, or who talked to whom, can still leak patterns. And if a device is already compromised by malware, decrypted data can be stolen at the moment it's displayed. Encryption is a powerful lock, but it isn't a cure-all. Misconceptions tend to cluster around 3 ideas. One is that all encryption is interchangeable, that the same method works everywhere. In reality, symmetric and asymmetric techniques play different roles. One is fast and shared. The other enables trust without a shared secret to start. Modern systems weave them together. Another misconception is that choosing a strong algorithm solves the whole problem. The math matters, and standards bodies like NIST publish guidance on what's considered secure today. But the bigger practical risk is key management. The best algorithm can't help if keys end up in a public repository or backups aren't encrypted. A third misunderstanding is that stored data is somehow safe by default. In many organizations, at rest, data concentrates value. The entire customer table, full backups, months of logs. A single breach can spill far more than a mid-flight interception ever could. Encrypting storage is not about checking a box. It's about protecting the most complete versions of information. The key idea is to build a simple mental checklist. Is data sealed when sitting still? Is it protected on the move? And are keys handled like the secrets they are? Bring this back to practical choices. On personal devices, enabling full disk encryption means a lost laptop doesn't become a data leak. On servers and in the cloud, turn on encryption for volumes, files, and databases. Many platforms offer server-side encryption that happens automatically when data is written. For applications, use mature libraries rather than inventing custom cryptography. In transit, use HTTPS everywhere for web traffic and encrypt internal service calls as well. Inside a company network, pretend the hallway is public. Make encryption the default, not the exception. One more layer, identity and authorization. Encrypting traffic with TLS ensures privacy and integrity, but it also hinges on trusting the right certificate. Using certificates issued by reputable authorities helps a browser verify it's connected to the real site. Internally, mutual TLS, where both client and server present certificates, can lock down service-to-service trust. Again, this folds back into key management, because those certificates depend on private keys that need careful handling. Where should keys live? Not in source code, not in spreadsheets. Dedicated key management systems and hardware security modules can generate and store keys in ways that make extraction hard, even for insiders. Cloud providers offer managed services for this, which can simplify rotation and access control. On the policy side, limit who can decrypt what. Separation of duties. Operators can run systems, but only specific roles can request decryption, reduces the impact of a single mistake or a stolen credential. Here's a small but important nuance about at-rest encryption. There's a difference between encrypting data on disk and encrypting data at the application layer. Disk encryption protects against someone walking off with the hardware or making a copy of raw storage. Application-level encryption can protect certain fields even from database administrators or cloud providers because the application controls the keys. The trade-off is complexity. Key distribution to applications and searching or indexing encrypted fields become harder. Matching the method to the threat model keeps complexity in check. In the transit world, a similar nuance shows up in certificate validation. A padlock icon doesn't guarantee the site is trustworthy. It guarantees the connection to that site is encrypted and that the certificate matches the domain. Phishing sites can still get certificates for lookalike domains. Human judgment and additional signals still matter. In other words, encryption is necessary, but not sufficient. It underpins trust on the internet and protects stored information, yet it works best as part of a broader security posture. Access controls, monitoring, patching, and good operational habits. To keep this grounded, return to the safe and the armored truck. The safe's lock is symmetric encryption at rest, fast and strong. The armored truck's handshake and paperwork at the depot are the asymmetric pieces that establish trust for the trip, with a symmetric shield once the journey begins. Security teams then manage the combinations and the paperwork, rotating them, revoking them, and logging who used them. If keys are left lying around, the rest doesn't matter. A few sensible habits go a long way. Turn on encryption for both states rather than choosing one. Schedule regular key rotation so old keys age out predictably. Monitor for accidental key exposure in code repositories and chat logs. Prefer up-to-date protocols like TLS 1.3, which streamline the handshake and remove weaker options. When performance becomes a concern, look at where asymmetric operations sit in the path and where hardware acceleration can help. These aren't exotic moves. They're the table stakes for handling valuable data. One last practical angle: incident response. If a team suspects a key has leaked, having a plan to revoke and replace matters more than the perfect algorithm choice. Short key lifetimes, automated rotation, and clear rollback steps make that moment survivable. The blast radius stays small because the window of exposure stays short. Standards exist to help with all of this. Organizations like the Internet Engineering Task Force define how protocols like TLS should behave, and agencies like NIST publish vetted algorithms and key management guidelines. Following those guardrails avoids pitfalls that come with homegrown shortcuts. If the entire topic had to be captured in one sentence, it would be this: encryption turns data into ciphertext that only the holder of the right key can turn back, whether that data is sitting still or traveling fast. To recap the mental model without getting lost in details, picture a safe and an armored truck. The safe protects stationary assets. The truck protects the journey. Both depend on the combination and the paperwork being handled with care. Translate that into the digital world, and the picture holds. Strong algorithms, smart protocols, and disciplined key management working together to keep information under control. If this helped clarify the big picture, a like and subscribe helps more videos like this reach the people who need them.